Introduction to the Delian Quest Revisited. The Delian Quest Revisited is a different type of novel which pairs all four members of our grammar matrix, used to find the answer to what I originally thought was an impossible problem to solve. For me, it was the foundation of putting me on the path to formal geometry, or metagrammar. In Euclid's Elements, one can see that a great deal of effort was put into solving equations using parallel lines, or parallelograms. However, those who worked on the elements never achieved an understanding of what the original authors of the book were aiming at. Ultimately, with human intelligence being what it is, it was determined that Plato's quest to codify geometry as a metagrammar was impossible. One of the reasons being is that those who worked on the elements put words into Plato's mouth that he never stated. In so doing, Euclidean geometry, as it was called, became a sport instead of the metagrammar Plato claimed it was. In Plato's day, instruments were not only primitive, algebra itself was not even a grammar system. Still, Plato was not shaken, for he knew what every computer has demonstrated globally today: all of our systems of grammar are binary, relatives, or verbs, contained by correlatives, or nouns. As binary recursion can only produce a binary result, all that is required is not to spin off into the bananosphere, but to keep investigating binary to learn how to use it. Let your assertions be assertions, and your denials be denials, for there is no third imaginary pucker between the two. Unfortunately, today, mankind is full of educational systems teaching not reasoning, but the art of imagining puckers. In the following proposition, one is being told to use what we learnt in Propositions Book 147, the so-called Pythagorean theorem, which is not a theory at all but a mathematical fact, or again, a simple equation, a squared equals b squared plus c squared, from which, given any two parts of the equation, one can determine the remainder, and Book 148, where every triangle can be divided into two right triangles. From there, we learn that any rectilinear figure can be reduced to a rectangle. This provides us with a standard method of constructing any rectilinear figure into two, and only two values, which reduces our work to simple and b. Book 2, Proposition 14. To construct a square equal to a given rectilinear figure. Let A be the given rectilinear figure. Thus, it is required to construct a square equal to the rectilinear figure A. I. 45. For let the be constructed the rectangular parallelogram BD equal to the rectilinear figure A. Then, if BE is equal to ED, that which was enjoined will have been done, for a square BD has been constructed equal to the rectilinear figure A. But, if not, one of the straight lines, BE, ED, is greater. Let BE be greater, and let it be produced, to F. Let EF be made equal to ED, and let BF be bisected at G. With center G, and distance one of the straight lines, GB, GF, let the semicircle, BHF, be described, let DE be produced, to H, and let GH be joined. 2. 5. Then, since the straight line, BF, has been cut into equal segments, at G, and into unequal segments, at E, the rectangle, contained by BE, EF, together with the square, on EG, is equal to the square, on GF. But, GF is equal to GH, therefore, the rectangle, BE, EF, together with the square, on GE, is equal to the square, on GH. I. 47. But, the squares, on HE, EG, are equal to the square, on GH, therefore, the rectangle, BEEF, together with the square on GE, is equal to the squares on HE, e.g. Let the square on GE be subtracted from each, therefore, the rectangle contained by BEEF, which remains, is equal to the square on EH. But the rectangle BEEF is BD, for EF is equal to ED. Therefore, the parallelogram BD is equal to the square on HE. And BD is equal to the rectilineal figure A. Therefore, the rectilineal figure A is also equal to the square which can be described on EH. Therefore, a square, namely, that which can be described on EH, has been constructed equal to the given rectilineal figure A. Therefore, given any rectilinear figure, we can determine its square root, or area. The following proposition is the simplified version of 2(14). Given any A and any B, to find their square root. Book 6, Proposition 13. To two given straight lines to find a mean proportional. Let A, B, BC be the two given straight lines, thus, it is required to find a mean proportional to AB, BC. Let them be placed in a straight line, and let the semicircle, ADC, be described on AC. Let BD be drawn from the point B, at right angles to the straight line, AC, and let AD, DC, be joined. 3:31. Since the angle, ADC, is an angle in a semicircle, it is right. And, since in the right-angle triangle, ADC, DB has been drawn from the right angle perpendicular to the base, therefore, DB is a mean proportional between the segments of the base, AB, BC. Vi. 8. Therefore, to the two given straight lines, AB, BC, a mean proportional, DB, has been found. Or again, given A times B, find the square root C. One can say, given any line with any point on it, if a semicircle is drawn to contain it, it means that we are multiplying and taking the root of the two given segments. I found it very odd, when I read a book on Cartesian geometry where it was asked, what is the equation of a circle, and then the author went off into the bananosphere and came up with the wrong answer, which is still repeated today, as if everyone is so illiterate, it is as if they never read the elements. So-called Cartesian geometry is very lame, very limited, and apparently the product of the illiterate. Both propositions tell you what the equation of a circle is, in terms of A and B. If you use Sketchpad to write the equation, the program itself will draw the circle.
Horse quotes are not only evil in themselves, that they infect the mind with evil. Phaedo by Plato,